So dear students, in the last class it's been discussed the master slave JK flip-flop. Here is the JK flip-flop. Now we'll look into the things that how we can construct the T flip-flop. T flip-flop will be built upon the JK flip-flop. J and K are the inputs and T will be shorted between J and K. When the T input is 0, so we are going to get both J and K is 0, 0. It's a previous state. When the T input is 1, both J and K will be 1, 1. It is toggle state. So if the previous output of Q is 0, then you'll be getting 1. If the previous output of Q is 1, then it will be 0. That's how the T flip-flop will work. The another name for the T flip-flop is the toggle flip-flop. Want to make this as a flip-flop, then it is mandate it should have a clock. So without a clock, it's called as a latch. So I'll be applying the positive edge triggered clock. Then if I want to write the flip-flop, then it is mandate I'll be having the clock input as well. So if I just represent this with an up arrow, it indicates it's a positive edge triggered clock. Otherwise, I can also write like this. Write the clock, highlight this positive edge. That is also a right way of representing the positive edge of the clock. So upon this JK, we know how to work with the T flip-flop. So you need to write this block diagram, the truth table. Either write one of this, okay? Don't write both of this. And then you have to write the timing diagram. How to write the timing diagram? First write the clock inputs. So here you know only two possible inputs. So you can just represent the clock. And this is the positive edge of the clock since I've written positive edge. And we know the truth table. So and also we know very clearly only T is the input. T will be either 0 or 1. So whatever the T input before the positive edge, for that it will be triggering. So it cannot, if the T changes exactly at this particular time instance, I can't get that output here. So if I'm writing T0, for this 0, what should be the output? That I can get it across this. That is how it will work. Okay. I'll just make I would have not done this at this particular instance of time. Let me write like this. So just write the input changes before the clock event. Be careful with this. Even when you do it, practically you should observe with these things. So input should be done before the event occurs. Otherwise, you can't get that changes in the same instance of time. So this is the positive edge of the clock, where your output changes based on the input what we provide. So here it is 0. For this 0, what should be the output? I just assume my Q was 1 before, okay? So because of this 0, so we'll be getting previous state, right? Whatever is there, same thing continues till the next event occurs. At this instance of time, it is 1. 1 means toggle. If my Q was 1 before, so it will be 0. So here at this particular instance of time, it was 0. 0 means same state, it continues. I would have written one more clock pulse. I think instead of writing here, I would have written the positive of the clock here, T here only. I think that would have given better idea for you how this will work. So let me do these changes. Yes. So let us focus on this at every positive edge of the clock. Okay. Let me retain my T high for 2 clock pulses together. Let it be like this. See, observe now. So clock, positive edge of the clock, T was 0. 0, previous state. Previous state of Q is 1. So it retains same till the next positive edge. So this, I hope it's understood for you. Now it is 1. 1 toggle. Toggle in the sense, if it is 1, then you will be having 0 till the next positive edge of the clock. Now again 1. 1 means toggle. Toggle in the sense, already it is 0. Now it will change to 1 till the next positive edge of the clock. Before that, the input here is 0. 0 previous state. Previous state, okay, retaining the same thing. This is how the T flip-flop will work. We'll look into that, the different ways of representing flip-flops. I'll just write it FF. So one of the way which has been discussed from the beginning is this symbolic representation, or I can call it as a block diagram. So another way of representing the flip-flop is this truth table. So these are the two different ways which we have discussed from the beginning, the symbolic representation and the truth table. So what is this truth table is, we'll be knowing what are the inputs. Okay, if these are the inputs, what is the output for this? Now another two ways of representing flip-flops are there. One is excitation table, and we'll call that as a characteristic equation, and one more is the state diagram. Okay, if this is the present state of the inputs, what is the, if this is the inputs and these are the present states, what will be the next states? So we are going to represent the state diagram and the characteristic equation and the excitation table. Normally we will not be writing this symbolic representation of the flip-flop because it will not give us any details there, it just represented there. But when we write this truth table, the excitation table, the characteristic equation and all those, we can able to represent the working of the flip-flop with that. That's the reason we'll be using those four methods: truth table, excitation table, state diagram and the characteristic equation. So here you just write down the entries. So for S and R, when we were having as inputs, we were writing four conditions: 0, 0, 0, 1, 1, 0 and 1, 1. Now we are including what is our previous state of the Q. It is not Q bar, it is N plus 1, the next state. If it is Qn is the present state, Qn plus 1 is the next state of the output. So these outputs are very important when we are working with the flip-flops, the present state and the next state. So you write down along with me. So Qn and Qn plus 1. So when there is 3 inputs, I will write all 8 combination: 000, 001, 010, 011, 100, 101, 110 and 111. So you need to remember the truth table of the SR flip-flop. Based on that, we are going to write it here. 0, 0 we know. When 0, 0 it is previous state. So 0, 1 it is reset. Reset whatever the previous condition, we never bother. 0, 1 reset. So write 0. So 0, 1 reset. So 0. 1, 0 set. So 1. 1, 0 set. So 1. 1, 1 forbidden. So this condition can be any output. So I'll write don't care. I can get 1 or 0. See, there is difficult for me to write here. You write down X here. Don't care. So this is the truth table only. What I have considered here is, if my previous state is this, what is my present state? That is what I try to compute. Now you compute the characteristic equation. I need to find out Qn plus 1. What is the answer for this expression? So use K-map, write the entries inside the map and start simplifying. Yes, I'll consider it as a most significant here. R and Qn here. So it's a 3 variable. So S, R and Qn, 3 variable. Write down the 3 variable map. 0, 0, 0, 1, 1, 1, 1, 0. Put the end, scan through this Qn plus 1 put the entries into the map. So 0th it is 0, 1 it is there, so 1, 2 is 0, 3 is 0, 4 it is 1, 5 it is 1, 6 and 7 it is don't care. So 6 and 7 it is don't care. So put the entries inside the map and do the grouping. So now do the grouping. This one, this is the only option, so I do this grouping. What's the expression? I got it here, R bar Qn. So Qn plus 1, answer is R bar Qn plus this. I can make it all 4 in one group, so I'll make this all 4 in one group. The result here is S. Instead of writing like this, I just rewrite this S plus R bar Qn is the expression for Qn plus 1. This is called as a characteristic equation of an SR flip-flop. Where I can use this characteristic equation, you all know that we have written an VHDL code when we want to simulate the hardware using an HDL. We have used an VHDL code. There I want to realize an SR flip-flop, suppose. How I realize an SR flip-flop? So I'll be knowing what is the present state of inputs, S and R inputs, and also since it is in sequential circuit, we know what is the previous output as required. So when I know what is the present state of input and the previous state of output, then I can able to find out what is the present output. This is the expression. So if I just realize this, a simple AND OR gates, yes, or not R and Qn. So that is the VHDL code for the SR flip-flop. I can just write like this. This will be assigned with yes or not R and Qn. So this is the VHDL code now. Very simple. I can able to implement this SR flip-flop in the using this characteristic equation. We just want to discuss with the JK. So it's similar to your SR. All these conditions retains the same. So this 0, 0, it's a previous condition. So previous state of the output is 0 and 1 are written. 0, 1 reset. So 0, 1, 0 set. So 1, 1, 1. It was forbidden in case of an SR flip-flop. Now it is toggle. The meaning of toggle here is when it is 1, 1, the previous state of the output is 0. Now it will be 1. So in the last case, 1, 1, the previous state of the output was 1. It will be 0 here. So it is less space. I'll just write down 0 here. So these are the J and K contents of the input, and Qn is the previous state. So we computed the next state. Now you need to compute the characteristic equation for the JK flip-flop. Scan through this Qn, write the entries here and do the grouping. So 0th location it is 0, 1th location it is 1, 2 and 3 it is 0, 0, 4, 5, 6 it is there. So 4, 5 and 6 it is there. 7 it is 0. So I'll leave it empty. Now do the grouping. So when you want to do the grouping now, you will not be getting 4 ones now. So for this one, this is the only option. So I do this grouping. If you look into this one, I have two options, either this or by folding the map, I can group with this. So that's the reason I'll not be grouping this first. So this only one option. So I'll group this first. So for this one, this is the only option. So I group this. The expression here is, this is J, K, Q, N. So the expression here is K bar Qn plus, for this, by folding the map, I can do this grouping. So the expression here is J Qn bar. J Qn bar. So I just rewrite this because J is the first input. So that's the reason I've just written J first. So J Qn bar plus K bar Qn. Yeah, this MSJK flip-flop. So what I stuck up in the morning is like when the clock is 0, suppose if my previous outputs are 0 and 1 here, 0 and 1 here, right? When the clock is 0, J and K input are 1, 0. So this 1 has been feeded back here. J is 1, the feedback is 1 here, and the clock, since the inverter has been connected 1 here, all the 3 inputs across this AND gate is 1. The output here is 1. Now this here it has been 0, this output is 0, 1 0 across this, so the output here is set. So the this first master output is set, 1 and 0 will be getting. This master will be triggered when the clock is 0. So the slave will not be working at that time of instance when the clock is 0. When the clock changes from 0 to 1, when the clock changes from 0 to 1, the slave started working now. So now the clock is 1, the master is inactive now, the slave is activated. So 1 here, so both the inputs of this AND gate is 1, and the inputs across this is 1 and 0. 1 and 1, the output here is 1. 0 and 1, the output here is 0. So 1, 0 across this SR latch. So I'll be getting set. So this is how the working of the master slave JK flip-flop. So you should remember that when the clock is 0, only the master is enabled. When the slave is, when the clock is 1, the slave is enabled. Whatever the action of the master, the slave will be copying when the clock is 1. But in the last explanation, what I have explained here is within the single clock pulse, in the positive edge, the master will be triggering. In the negative edge, the slave will be triggering. Only one at a time. Since both are happening at the same clock, so once we apply the clock, we can able to observe the changes across the slave, because they will not be monitoring any output across the master. Is that clear? Fine. So we'll just continue with these things, because we were discussing the JK flip-flop. That's the reason I just discussed with master slave JK the master slave JK flip-flop, how we are going to represent and how it is working. Now we'll continue with the D flip-flop. What is the characteristic equation of the D flip-flop? Then the T flip-flop, what is the characteristic equation of the T flip-flop as well? So write down for the D flip-flop. You know the inputs for the D flip-flop is only one D input, and since I am writing here what is the previous state of the output, so D and Qn I will be writing Qn plus 1. So 0 0 0 1 1 0 1 1. So in this case, what is the present output? So when D is 0, it is 0. We never bother about what is the previous condition at all in the D flip-flop. Output follows the input. D0 0, D1 it is 1. So this is the truth table now. I need to compute the characteristic equation for it. So just write down the characteristic equation. So it is just a 2 variable only. Okay, here it is. So this is the expression for Qn plus 1. Here it is D, here it is Qn. So 0 1 0 1. The entries here is 0 location 0, 1 location 0. 2 and 3 it is there. So 2 and 3 it is there. You write down. Do the grouping. Only one group. So Qn plus 1 is D. That's it. If I want to write this VHDL code, very simple now. Qn plus 1 will be assigned with D. That's it. So now we'll look into the T flip-flop. So what's the change here is T. That's it. T is the input. So here I'll write T. I would have erased this also. Yes. So now single input. Qn is the previous state. Qn plus 1 is the next state. When T is 0, the output is previous state. Whatever your Qn, you should write the same thing here. When T is 0, it is previous state. So it is 1 year. When T is 1, the output is toggle. When T is 1, it is toggle. So 0 in the previous state. So now it is 1. So 1 in the previous state. So it is 0. This is the truth table of the T flip-flop. So write the entries into the key map now. So 0, 1, 1, 0. So you have written the entries. Do the grouping. So you can't do the grouping here. So it is diagonally been written here, right? So you can't do the grouping, individual, isolated ones. So when it is an isolated ones, it can't be unattended. It has to be grouped. When I group this, the expression here is T Qn plus here. So it is not T bar Qn. Here it is T Qn bar. T Qn bar. If you want, you can rewrite this. I don't think it will make any changes here, but you should know this complementary input and the previous output, or present input complementary of the previous output. So write the VHDL code for this, not T and Qn, so or with T and not Qn. This is the VHDL code for the T flip-flop. So in this you can observe what is the characteristic equation. This equation is important. Where we can use this equation is in order to represent the, or in order to implement this in the HDL. It need not to be in the VHDL alone. It can be in the Verilog as well. But right now you are learning VHDL. That's the reason I have written the VHDL code for the T flip-flop. So any doubts in this? Fine. Yeah, we'll just continue now. So we know the truth table and we have discussed the characteristic equation. Now we'll look into the state transition diagram. Then we'll write the excitation table. Okay. Now I just go it in the reverse order because T flip-flop is already here. I'll just write with the T flip-flop. Then I'll go for the D, SR and JK. So now the present state of the the outputs we are going to represent here. So what are the different outputs that's possible here? Or only two states, either 0 or 1. These are the two possible outputs. Now I'll be writing what state I'll be getting every time. Okay, just observe here. So outputs 0. I was in 0. So just focus these two. I was in 0. I get the 0. So I was in 0. I'll get 0. The arrow mark is important. I was in 0. I get 0 when my input is 0. When my T input is 0. So I was in 1. I'll get 1 when it is 0. So I was in 1. I'll get 1 when it is 0. Now I was in 0. I'll get 1. So I was in 0. I'll get 1 when my T is 1. So when T is 1, this is what the output I'm getting. I was in 1. I'll get 0 when it is 1. I was in 1. I'll get 0 when it is 1. This is called as a state transition diagram or state diagram. So you can get a question like state diagram or state transition diagram. So for any of the questions, this is the only answer. Now you know truth table, you know characteristic equation, and we have learned what is the state diagram. Now we'll just write the excitation table for this T flip-flop. Okay. Before I go with that excitation table, I just need to tell you few things. What is an excitation table? And many a times you will be getting confused with the truth table and excitation table. Truth table where you know the inputs. Okay, if these are the inputs 0 0 0 1 like this, these are the inputs, the output will be like this. This you are computing it. You already know the inputs, you are computing the output. Excitation table is reverse to this. You know, okay, what is the output you'll be getting. In order to get this output, what should be the input? So it's like a reverse. You'll be computing the inputs by knowing what is the output. Okay. So in order to write the excitation table easily, so what I'll tell is, we'll just make use of this state table or the state diagram. It would be easy to write the excitation table easily. I'll just erase this and I'll write it here only. The outputs are Qn plus 1. What should be the input? So 0 0 0 1 1 0 1 1. These are the different outputs possible. When it was 0, it can be 0. When it was 1, it can be 1. When it is 1, 0, 1, 1. What should be the input in order to get these outputs? So very easy to do this with the help of the state diagram now. So both are 0 0 0. 0 to 0 transition when it is 0. So I'll write 0 here. 0 to 1. 0 to 1 when it was 0. So this 1 0. 1 to 0 when it is 1. So 1 here. 1 to 1. 1 to 1 when it was 0. So 0. This is the, I think somewhere wrong, no. Yeah. So this is the excitation table of the T flip-flop. 0 to 0 when it was 0, 0 to 1 when it was 0, 1 to 0 when it was 0, 1 to 1 when it was 1. I think somewhere we did a wrong in the previous one. Sorry. This one. Then 0 to 1, this is 1 then. It's not a truth table, it's an excitation table. This excitation table and truth table look same here. So 0 0 0 1 1 0 1 1. So 0 0, it's a previous state, so 0 and 1. So it's a toggle 1 and 0. Yes, 0 to 0 transition it is 0, 1 to 1 transition it is 0, 0 to 1 transition it is 1, 1 to 0 transition it is 1. Yes, so there is no difference in the excitation table and the truth table of the T flip-flop, because it is working like 0 0 it is previous condition, 1 1 it is toggle. Even your excitation table looks the same. Similarly, you can work with the D flip-flop now. Start writing along with me. See, for the D flip-flop, 0 0 0 1 1 0 1 1. So the outputs are like output follows the input. When D was 0, it is 0. When D was 1, it is 1. Now the state transition diagram, 0 to 0 when it is 0. So 0 to 0 when it is 0. 1 to 0 when it is 0. 1 to 0 when it is 0. 0 to 1. So 0 to 1 when D was 1. 1 to 1 when D was 1. This is the state transition diagram for the D flip-flop. Now write down the excitation table. Now outputs are known 0 0 0 1 like that. I need to compute the inputs. So 0 to 0 transition when D is 0. 0 to 1 transition when D is 1. This is D. 1 to 0 transition when D is 0. 1 to 1 transition when D is 1. So now the truth table and the excitation table does not look same in case of the D flip-flop. Is that clear? Can I go to the next? Now we'll write it for the SR flip-flop and then do it for the JK flip-flop. You can also start writing along with me. I think this I need to write little smaller. I would have erased everything together. Fine. So yes, R Qn plus 1. So these two cases are previous state. Here it is reset. Here it is set. These two are invalid, like undetermined. This is the truth table. Now we'll write the state diagram. So I'll be writing all the cases, so I just need the space. So I'm writing little smaller. Then you can start writing. I'll be writing the excitation table. So now 0 to 0 transition when S and R was 0 0. 0 to 0 transition. So I forget to write this. Then I'll use different color. So 0 to 0 transition when S and R is 0 0. 1 to 1 transition when S and R is 0 0. When S and R is 0 0, it is 1 to 1 transition. 0 to 0 transition when S is 0, R is 1. 0 to 0 when S is 0, R is 1. 1 to 0. 1 to 0. 1 to 0 when S is 0, R is 1. 0 to 1. So 0 to 1 when S is 1, R is 0. When S is 1, R is 0. 1 to 1. 1 to 1 when S is 1, R is 0. Here it is 0 to don't care. That I can't write because that condition will never occur. 1 to don't care. That condition will never occur. So my SR flip-flop state transition diagram is only so much. Now we need to write the excitation table. Look into this and write down this. So please pay attention here. It's not so simple here. In the last two cases we have not considered here, and in order to transfer the state transition diagram to an excitation table now, when Qn and Qn plus was 0 0, so 0 to 0 transition, when S is 0, in both the case R is changing, means R is don't care. So S is 0, R is don't care. Next, 0 to 1 transition, 0 to 1 transition, when S and R was 1 0. So write down 1 0. 1 to 0 transition, 1 to 0 transition, when S is 0, R is 1. When S is 0, R is 1. Now, 1 to 1 transition, when S is changing here. So, S is don't care, R is 0. I can write R 0. So, initially when you are doing it for the first time, you follow this. Right? You remember the truth table. So, based on that, you write it for the present state of the output and compute the next state. Then write the state transition diagram. Then write the excitation table. It would be easy for you to learn it. Later part, you can just learn this excitation table, because this is very important. Based on the excitation table, we are going to design the counters that you will be learning in the next upcoming topics. Any doubts in this? So I'll just go with the JK flip-flop now. I'll erase this and write for the JK. So here it is. Sorry for this. So what's the change for the JK? You all start writing. Only the last two cases will change for JK. So 0 0 0, all these things retain same. When it was 1 1, it is toggle. So previous state is 0, the next state will be 1. When the previous state is 1, the next state will be 0. So this J and K inputs, this J and K inputs, that's it. So all these things we have already written. Just look into the last two cases. Instead of don't cares, we have 1 0 value now. 0 to 1 change. 0 to 1 change when J and K was 1 1. So write down 1 1 here. 1 to 0 change. 1 to 0 change when J and K was 1 1. Now when we are doing here 0 to 1, 1 to 0, there was only one entry earlier. Now we have two entries now. So that component will change now. So the middle entries will change. These things, just upgrade those changes, that's it. So now 0 to 0, 0 don't care. 0 to 1, 0 to 1, you're 1 here. So 1 don't care. 1 to 0, 1 to 0, don't care 1. 1 to 1, don't care 0. This is the excitation table of the JK flip-flop. Any doubts in this? Yeah. So you have to remember the excitation table of all the flip-flops. So where these flip-flops can be used in the counter design and in the CPLD reports you generate, right? When you simulate in the Xilinx, there also this toggle flip-flop has been used internally in order to build that. So with respect to the lab experiments, we'll be using this JK flip-flop to realize the sequential counters. So already we have done this counters. With respect to the decade counter, I hope you remember. Inside the decade counter, I see we have two mods, mod 2 and mod 5. Cascading that, we are going to realize that there also we use a JK flip-flop. But there will not bother much about the characteristics of the JK flip-flop there. We just use the toggle conditions always. So when J and K both are 1 1, whatever your inputs based on the clock which we apply, so it's going to trigger and we are going to get the discrete states based on the counter which we are realizing. But now here what we are going to, not now. So in the sequential counters, the counters will be asked like to design. The normal way of designing the counter will not use this internal details of the JK. If you know the truth table is fine. But the counter will be given like, the counter normally what we do, keep counting from 0 to some value. The counter will not be given like that. So counter will be asked like discrete states in between, like 0 it should start, then 5, 6, like 7, like that it should count. So in between, like it's not in a sequence, then how you will design the counter? In order to design the counter, the outputs are known for us. So after 0 it should be 6, then 5, then 3, then 7, like that we know what is the output. What should be the input in order to get that particular sequence of count? Then we go with this JK flip-flop. It's not necessarily only JK. We can make use of SR flip-flop, D flip-flop as well. But more preferably it will be used JK. So we'll be using JK only in order to solve the sequential counters in the lab as well. If these things are clear for you, then we can move on for the counters. So I'll not be discussing details of the counters now. We'll just look into the things how we can count it. Okay, if these are the counters, 3-bit counters, suppose this is the counter, I start counting from 0, it just goes sequentially 0, 1, 2, 3, like that. I sequentially do the counting. Then you can design it easily now. Take down this. So it just follows the sequence 0, 1, 2, 3, 4, 5, 6, 7 and 0. So it's keep counting. Now we'll just do the modifications in the counter. Let it not be 0 to 7 because by default when it is a 3-bit, it is 0 to 7. I want to design it for a different counter. Let it count 0, 1, 3, 4, 0, 1, 2, 3, 4 and then 0. Only 0 to 4. Then if it is counting from 0 to 4, what I call it as mod 5 counter. If it is counting from 0 to 5, then it is mod 6 counter. Like that I keep counting based on whatever the mod given. So now we need to design for this. So what is known for us now? What are all the counts it has to do it? So output is known. So first all 000, next 001, next 010, 011, 100. After this it should be 000. So this is how it should count. I know the output now. What should be the input now? I need to compute that input. In this case we'll use this JK flip-flop. Not only JK, also it can be specified to implement this with SR flip-flop or D flip-flop. You should be able to do it. So this question can come in the theory like design the counter with any sequence of the count using what particular flip-flop they have asked, use that flip-flop and design it. Or else in the lab exam you will be having only with JK flip-flop. So now you can start doing this design of the counter for the sequence mod 8. Mod 8 means 0 to 7 it should count. Can you all start writing now? Before that, tell me, in order to design this counter, how many flip-flops are required? Can anybody answer for this question? How many flip-flops? One flip-flop can store 1 bit of information. So here we have 3 bits, so 3 flip-flops are required. So we'll be having 3 flip-flops. So here, this is the most significant bit, this is the least significant bit. So most significant bit, where you will be writing, that decides the design of the flip-flop. So it's not mandate that where to write the most significant bit, where to write the least significant bit. But you should be very careful. This is the most significant bit. If I'm naming this as A, your truth table will be like ABC. Then the flip-flops, you can write it in any way. The inputs may vary. Or else I can write this as CBA. I just want to make it A as the least bit. So your implementation will be like this. So you decide what you use it here. So be careful with the inputs. It's not necessarily this, but you compute the inputs there, based on that you write. Why I'm telling this? Because you just observe what is the most significant bit, what are the inputs you computed for that flip-flop, based on that you write it. Blindly, if you are copying one page, you'll copy the truth table from somebody else will copy your circuit diagram. If these two are not matching, then entire things will go wrong. Be careful what you are going to write there. Okay. The reason why I've written this CBA, because if you observe the decade counter, what we have already written, we make there the D is the most significant bit, A is the least significant bit. So if you just want to follow the same thing with respect to the flip-flops, synchronous counter as well, you just follow the CBA. Otherwise, you can just follow ABC. It's up to you what you will decide. Is that clear? Just take down the lab problem. We'll start working with the lab problem only. Design a synchronous up counter. Design a synchronous up counter which counts, or a 3-bit synchronous up counter. Better you write that. Design a synchronous 3-bit up counter. So what is the meaning of synchronous? Yes. Synchronous, asynchronous, because these two words are again very important. Sequential, combinational, these two also again very important. So synchronous, it's synchronized with respect to the clock. Asynchronous, the output of the previous stage will be triggering the next one. Only the clock has been provided, only the first stage. This is how it is. So same clock has been provided for all the flip-flops. So outputs we are extracting like this. So now, what is the delay in this? The delay of this flip-flop, sorry, the delay of this counter. If it is a sequential and it is a synchronized with respect to the clock, everything is working at a time. So delay of one flip-flop, I don't know what is the delay of one flip-flop. It will be in terms of some nanoseconds. So delay of one flip-flop is the delay of this entire circuit, because the same delay applies for everything here. But here, the delay of the circuit will be like whatever the delay of one flip-flop into how many such flip-flops. Here, the delay of 1 into 3, because it is 3 flip-flops here, or I can call it as the delay is additive here. You keep adding the delay of every flip-flop together in order to find the delay of this entire circuit. So these are the differences between the synchronous and asynchronous counter. Synchronous, the simultaneous clock has been provided for all. Asynchronous, output of the first stage will be provided as a clock for the second stage is 1 point. Second point, the delay in the synchronous is the delay of a single flip-flop. Delay in the asynchronous is summative or summation of the delay of all the flip-flops. Then both of this we can able to design any counter, up counter or down counter we can able to design. Even the discrete states, like if I want this particular state, then the next here in the synchronous I can easily design. Asynchronous, it is little hard to design if it is a different states or is a sequence. Okay, it's not continuous, then it is little tough to design in the asynchronous. But one more thing, the designing with respect to the continuous sequences, then asynchronous is very simple. We need not to bother much, just keep delaying the the clock input. I can able to design asynchronous easily. Designing the synchronous will take more time, and not only the more time, designing of synchronous is little complex when we compare with the asynchronous, and it is costlier as well. The designing of synchronous is costlier because we need more additional circuitry in order to design for different counts of sequence. So these are all the differences between the synchronous and asynchronous sequential circuits. So sequential and combinational, I already told you the difference. Sequential, so output depends on the present input and the previous output. Combinational, output depends only on the present input. So you can write down the example. Sequential, you can write down counters, registers, flip-flops, all these are sequential. Combinational, you can write adders, this code converter, multiplexers, all those are the combinational logic circuits. So with these things, I'll wind up the today's session.